Welcome to The Explainer. Okay, what if I told you there's a simple, elegant way to find the absolute shortest number of steps between 2 points in a network every single time? Well, that's exactly what we're breaking down today. One of the most fundamental algorithms out there, breadth first search, or as you'll hear it called, BFS. So let's start with this very question, because this problem, it shows up everywhere. It's in your mapping apps, it's how data gets routed across the internet, and yeah, it is an absolute classic in coding interviews. The question itself sounds easy, but finding the answer efficiently, that's the real trick.
If you want to get the intuition behind BFS, this is it. This is the mental model you need. It's an algorithm that explores outward from a single point, just one layer at a time, exactly like ripples on water. It never skips a layer to go deeper. And that one simple idea is what makes it so incredibly powerful. So let's dive in.
All right, so what is BFS, formally speaking? We've got the ripple idea down. Now let's put a proper definition on it. It's a graph traversal algorithm, but it has a very specific and very powerful way of getting things done.
The crucial takeaway here is that it systematically explores level by level. So it visits all the immediate neighbors first. That's level 1. Then it visits all of their neighbors, level 2, and so on and so on. This methodical, patient approach is exactly what guarantees it finds the shortest path, at least in terms of steps, for any graph where each step is equal. No exceptions.
And, this isn't some hot new idea that just came out. Its core principles have been solving real-world problems for over 60 years. We're talking about things like finding the fastest way out of a maze or figuring out how to route wires on early circuit boards. It's a true classic, a real workhorse of computer science.
Okay, so let's get into the mechanics of it. How does this algorithm actually keep track of all those layers? How does it enforce that strict level-by-level rule without getting lost or jumping ahead? What's the secret sauce?
Well, the secret weapon behind BFS is a surprisingly simple data structure called a queue. And you only need to know one thing about a queue. First in, first out. FIFO, just like a line at the grocery store. The first person to get in line is the first person to check out. That simple rule is what perfectly enforces the level-by-level exploration. It's pretty brilliant.
And this right here, this is the whole dance. It's just a simple, elegant loop. You start with your source node, you pull it from the front of the line, you check it out, and then you add all of its neighbors that you haven't seen yet to the back of the line. That's it? This process ensures you finish exploring the entire current level before you ever even touch the next one.
So we know the why and we know the how. Now let's dig into the what. The key guarantees and the little details you need to remember when you actually sit down to implement this thing. This is the big promise, the absolute guarantee of BFS. Because you're exploring layer by layer, the very first time you pull any node out of that queue to process it, you can be 100% certain that you have found the path with the fewest number of steps to get there. There's just no way you could have reached it faster.
Now pay attention here, because this is a classic interview trap. The question is, when do you mark a node as visited? See, if you wait until you pull it out of the queue, you could end up adding the same node to the queue multiple times if different paths lead to it. That's just wasted work. The correct, most efficient way is to mark a node as visited the instant you add it to the queue. That way it's locked in and you'll never add it a second time.
Okay, so we know it works, we know it's reliable, but is it fast? Is it efficient? Let's talk about performance, or what we in computer science call complexity.
For a standard graph, the time it takes is proportional to v plus e. So v is the number of vertices or nodes, and e is the number of edges or connections. This makes sense, right? You have to visit every node and check every connection once. The memory or space it takes up is proportional to v. Now for something simpler, like a tree, the time is based on n, the number of nodes, but the space it needs is based on w, the tree's maximum width, which is an interesting detail.
Yeah, and this difference in space usage is a really big deal. For a tree, the queue only ever has to be as big as the tree's widest point. So if you have a tall, skinny tree, that's not much memory at all. But in a very dense, interconnected graph, where everything's connected to everything else, your queue might, in the worst case, have to hold almost every single vertex at once. And that's a key trade-off you have to keep in mind.
So, why does any of this really matter? When you're in an interview or working on a real project, when do you actually reach into your toolbox and pull out BFS?
The answer is actually pretty simple. You use BFS anytime you need the shortest path in terms of steps, and every one of those steps has the same cost. So think about finding the fewest number of moves to solve a puzzle,
or the shortest word ladder to get from cat to dog, or even just visiting every part of a network level by level.
And that brings us to the classic showdown, BFS versus its cousin, Depth First Search, or DFS. They're really two sides of the same coin. BFS explores wide using a queue and guarantees you that shortest path. DFS explores deep, diving down one path as far as it can go, usually with a stack. It's often more memory efficient, but it gives you zero promises about finding the shortest path. So, if you need the shortest path, BFS is your tool, hands down.
So if you remember nothing else from this explainer, let it be these three things. 1. BFS explores in layers, like those ripples on a pond. 2. It absolutely guarantees the shortest path when all steps are equal. And 3. The whole thing is powered by a simple first-in, first-out queue. That's the magic.
The answer, of course, is you set up your queue. You know exactly where to start. You now have the mental model to tackle that problem with complete confidence. Thanks for watching.